Hi everyone, welcome to Power Electronics session 17. So we completed all the theory portion in inverters. Now we will discuss some questions from the previous gate exams as well as some other practice questions. Okay, we'll see that. The first question is, a bridge inverter is fed from 300 volts DC supply and is operated at 50 Hz. It is connected to a load having 20 ohm resistance and 0.5 Henry inductance. The peak current in the circuit is okay. So here the bridge inverter is given, means it is full bridge inverter only by default. So here resistance is given and inductance is given, so you can take whichever the values are actually given here. So this is R and L. So we discussed about the peak value in case of RL load. What is the peak value in the RL load? I naught max is, if you remember, it is VDC by R into tan H T by 4 tau. I don't know how many people remember that. Okay, so here, so like T is nothing but 1 by F and tau is nothing but load time constant, that's L by R. Okay, you can substitute everything and get the maximum value. So I naught max is VDC 300 volts by resistance is 20 tan H 1 by, because T is actually 1 by F you can take it in the down, that means 50 into 4 into L by R comes to the numerator. R comes to the numerator means this is 20 and L is 0.5 Henry. Okay, so this is what we need to take. So 300 by 20 is nothing but 15, and tan HX, H of this one is like a 0.197. Okay, so if you take the equivalent of this is 2.96 ampere. Okay, then move on to the question number 2. So a single phase full bridge inverter has RLC series load with a 10 ohm resistance XL omega L. It means omega L 9.89 ohm XC, that's nothing but 1 by omega C, 28 ohm. The DC input is 230 volts. The RMS value of the load current at the fundamental frequency is, okay, so here it is like RLC series load is given. Okay, RLC series load. Okay, so now it is asked about the fundamental frequency component. Fundamental frequency component means we need to consider V01 and all. Okay, so here resistance is given, omega L is given, 1 by omega C is given. So now we need to calculate what is the I01. To calculate I01, we need to take, as we discussed already, I01 is nothing but V01 divided by Z1. Okay, how to calculate the V01? We already discussed V01 is nothing but 0.9 times VDC by Z1 is nothing but root of R square plus omega L minus 1 by omega C whole square. Okay, that's what we need to substitute everything and get the fundamental RMS current. So that's nothing but 0.9 into 230 divided by root of R square is nothing but 28 square. Sorry, R square is 100 plus omega L is 29.89 minus, we need to substitute 28 whole square. So if you take the equivalent of this is 9.96, approximately 10 ampere. Okay, so that is for the second question. Now come to the third question. Okay, so a single phase full bridge inverter has RL load with a 10 ohm resistance and 25 millihenry inductance. The switching frequency is 60 Hz. The input voltage to the inverter is 100 volts. Calculate the average value of the source current. Okay, to calculate the average value of the source current, we already discussed. Okay, so to calculate this, we require average DC current is nothing but power consumed by the load divided by VDC. But how to calculate the power consumed by the load? That is the one mainly we need to calculate. So that means I naught RMS square into resistance. So basically we need to calculate the RMS value. As I told you that RMS value we need to calculate by using different components. I naught RMS equal to square root of I01 square plus I03 square plus I05 square. Approximately can go only 4 components. Okay, so this is what we need to consider. So but how to calculate the I01? I already told you we need to calculate the Z1, Z2, Z1, Z3, Z5, Z7. So once you know that, you can easily do that. Okay, so first we will calculate the impedances, then it is easy to calculate other things. How to calculate the Z? So as I already told you, Z1 is nothing but a root of R square, that's nothing but like here, plus omega L whole square. Okay, that we need to calculate. Z3, same thing, R square plus 3 omega L. We need to substitute everything and need to get this one. So likewise Z5, Z7. Once you know these things, then you can calculate the RMS current by using means we need to get the I01, I03, I07. What is I01? I01 is nothing but V01 divided by Z1, what you are going to get here. I already told you V01 is nothing but for the full bridge inverter 0.9 VDC. So you can take that, okay, equivalent values and get the I01. Likewise I03 we need to get, that's nothing but V03 by Z3. That I also told you that V01 divided by 3Z1, that means 0.9 VDC by 3 times Z3. That's what we need to calculate. Likewise, we need to go for I05. I05 is V05 divided by 5 times Z3. So Z5. So likewise, we need to calculate. So if you substitute the values and calculate Z1 13.74, Z3 31, Z5 48.174, Z7 66.73, that means every time we need to keep that omega here reduced. So 1 time omega, 3 times omega here, 5 times omega here, 7 times omega. This is only the main issue to calculate. Once you got this, then you can calculate I01 is that V01 by Z1, then it will give 6.55 ampere. Then I03, that means third harmonic current RMS value, V03 is nothing but V1 divided by 3. That's a V03. by Z3, then it's approximately 1 ampere. Likewise, we need to calculate I01, I03, I05, I07. Once you got this, we need to substitute here. Once you substitute this, then you can get the RMS value, approximate value. So if you substitute all these values here in this equation, then you will get approximate current is 6.64 amperes. So once you got this, then we need to proceed further. So proceed further is nothing but we need to calculate power consumed by the load, that is nothing but I square RMS value, that means 6.64 square into resistance, that is nothing but 10 ohm. So 10 ohm is resistance, then it will give you the power. So we get 440.73 watts. From this you can calculate the average value of the source current. IDC is nothing but power consumed by load 440.73 watts divided by source voltage, that's nothing but 100 volts. That means current is 4.4073 ampere. Okay, so this is what you can calculate. So now from this you can also calculate few other things. That's what we are going to discuss now. So I'm taking that I01 and RMS current. With these things you can calculate lot of other things. Okay, so from the previous example we got the total load current RMS value this much and fundamental current this much. Now we can see that almost this current is very close. So from this we can calculate current distortion factor for the load. Current distortion factor in the load is nothing but 6.55 divided by 6.64. Okay, so what's the value? It is 0.986. So 0.986. So that means it's very close to 100%. That means harmonic content is reduced. That is because of the inductance. If inductance is not there, this will also be 0.9. So that is advantage. If you have the inductance, it will filter out the values. So now you can see other thing is percentage THD. This indicates that how much content, harmonic content is there in the load current. Remember, in case of like a single phase inverters, voltage will not depend on the any current waveform, any load. That's why it is always square wave. Square wave will always have the 40.34%. But now here inductance is connected. With that, how much harmonic content is filtered out, we can see now. So this is root of 1 by 0.986 square minus 1. So we need to get the value. So this is 16.56%. So now look at that. This is reduced from 40.34% to 16%, 16.56%. Okay, so 56%. This is because of the inductance. If you keep on increasing this inductance, this will further decrease. So that's what. Suppose if you want to calculate the power factor, load power factor, we can also do that with the help of this one. That's what I'm telling, that this type of question can give it as a linked questions. That means it's a big process. That's why once you got the I0 RMS, we can calculate other things also. That's why you can actually consider this one as a linked questions in the GATE exam. Load power factor, using this information, load power factor PF equal to power consumed by the load divided by V0 RMS into I0 RMS. So V0 power consumed by the load we already calculated 440.73 watts divided by RMS value of the load voltage is nothing but DC for the full bridge inverter. I0 RMS just now we calculated 6.64. Then it will give the power factor value. So it is 0.664 lagging. Okay, so that's what we can calculate if you know the RMS value of the load current. So this is a procedure. Even though it's a lengthy procedure, we need to practice this one. Okay, sometimes if you want to calculate the approximate values with a little bit difference in the decimal point, I not RMS we can calculate using third harmonic and fifth harmonic. That's sufficient. No need to go further. Okay, that means fundamental component, third harmonic, fifth harmonic. If you get possible time, then go for the seventh harmonic, then we will get the proper values. Okay, then move on to the next question. A single phase voltage source inverter is feeding a purely inductive load as shown in figure. Purely inductive load means proper inductance here. The inverter is operated at 50 Hz in 180-degree square wave mode. Assume that the load current does not have any DC component. The peak value of the inductor current. So here you need to remember two things. It is operating in 180-degree square wave mode. Operating in 180-degree square wave mode is nothing but it is like perfect square wave. Okay, perfect square wave. Square wave mode, I already told you that it is operating like a perfect square wave. It is not operating as like a kind of voltage control mode, like a pulse width modulation. That's the meaning. And assume that load current does not have any DC component. Nothing but it's like a proper AC current. Proper AC current is that means I told you that for pure inductor it is nothing but triangular waveform. Like that. So pure AC is nothing but this max and this max must be same, but in opposite direction. That's okay. So that's the meaning of A and does not have any DC component means. We already discussed the equation for this. Maximum load current for this pure inductor is nothing but VDC by 4FL. 4FL. So now you can substitute here. VDC is 200 volts and 4 into F is 50 Hz. It is already given. It is operating in 50 Hz and L is 0.1. Okay, so that means this is 5. Okay, and 4 into 520, that means 10 ampere. So that's one. Okay, so move on to the next question. In the converter circuit shown below, the switches are controlled such that load voltage V0 of T is 400 square wave. Okay, square wave. The RMS value of the fundamental component. It's a full bridge inverter and operating in 180 degree because nothing is given here means 180 degrees. In case of 180 degree, what will be the RMS value of the fundamental voltage? Nothing but V01. V01 is 0.9 VDC. That's it. Nothing else. But remember, RMS value I already told you will not depend on the frequency. Frequency will be different. That won't change. Only the RMS value of any voltage waveform depending on the shape of the waveform. That's why here nothing is actually impacted by that. So here 0.9 and 200. So we need to take that one. So 220 into 0.9, that is equal to 198 volts. Next, a constant current source inverter supplies 20 ampere to a load resistance of 1 ohm to load resistance of 5 ohm, then the load current is. You can see all the options, but here it is given a CSI. Okay, remember it is CSI. Okay, what I told you in case of CSI I told you CSI is nothing but I say like that. What I can say like it is dual of the VSI. Okay, it is dual of VSI. So it is dual of VSI. That means here in case of CSI, load current will be independent of the load. Okay, will be independent of the load. If load current is independent of the load, now the load is changing from 1 ohm to 5 ohm. If load resistance is changing from 1 ohm to 5 ohm means load current is independent of the load, then in that case what will happen? It remains same at 20 ampere. So remains same at 20 ampere. But load voltage in case of CSI depends on the load. So that's why here load current is same means It earlier it will be 20 into 1 ohm is the voltage. Now 5 ohm is there. That's why it will become 100 volts. That's why this is related to first option. Okay, move on to the next question. A three-phase voltage source inverter is operated in 180-degree conduction mode. Which one of the following statement is true? Both pole voltage and line voltage will have third harmonic component. Pole voltage will have third harmonic component, but line voltage will be free from third harmonic. Line voltage will have third harmonic component, but pole voltage will be free from third harmonic. Both pole voltage and line voltage will be free from third harmonics. Okay, remember in 180-degree mode conduction we discussed we discussed something to answer this question only. That's nothing but I told you like this arrangement is required to answer one of the gate question. That's nothing but voltage divider, like a capacitor potential divider we have taken. Okay, right. If you look at that video, you can again see that. That's where we discussed about the pole voltage and line voltage. Okay, pole voltage is actually, in case of 180-degree mode, it is square wave. Okay, and line voltage is, it's a cos square wave. Okay, so cos square wave with cosinus 60 degrees means it is only will have the all odd harmonics except triplet harmonics. Nothing but 1, 5, 7, 11 and so on. Okay, but here perfect square wave will have all odd harmonics. That means 1, 3, 5, 7, 9, 11 and so on. So this is the pole voltage, this is line voltage. So now we can see that what's the answer for this. Okay, pole voltage will have the third harmonic, but line will not have that. That's why answer will be pole voltage will have third harmonic, but line voltage will be. That means this is the answer. Next, a three-phase voltage source inverter with ideal devices operating in 180-degree conduction mode is feeding a balanced star connected resistive load. The DC voltage input voltage is VDC. The peak value of the fundamental component of the phase voltage is. Okay, so here we need to know that what is the maximum value of the fundamental component of the phase voltage. But here to answer this question we need to know that what is this way, like a operating mode, or what configuration it is given. It is given 120-degree conduction and it is given star connection. Okay, so remember, so in case of 180-degree star connection we discussed Fourier series for line only. That means VAB is sigma n equal to 135 infinity 4 VDC by n pi sin n, okay, n pi by 3 into sin n omega t plus n pi by 6. This is what we discussed. Okay, this can be replaced with the cos also. Cos n pi by 6 will be there. Now in this is a line voltage. I am not telling that every time line and all. So remember V01 line substitute n equal to 1. Okay, this is still the instantaneous value. 4 VDC by pi sin pi by 3 sin omega t plus pi by 6. It is asked about maximum value. So what's the maximum value of the line voltage fundamental value? So except time quantity, everything comes under line. That means 4 VDC by pi sin pi by 3 sin 60. What is the sin 60? It is root 3 by 2. Okay, leave it like that. So What is the connection is given here? It is a star connection. What is the relation between star connection, voltage, phase voltage and line voltage? Because it is asked about peak value of fundamental component. Yes, fundamental component, peak value. That's why we have taken only maximum value. And then asked about the phase. So, but we actually got the line. So, how to get the phase voltage, fundamental value? That is, relation between the line and phase in case of star connection is phase voltage is nothing but line voltage divided by root 3. That means 4 VDC by pi into root 3 by 2 whole divided by root 3. So here root 3 gets cancelled, and then 2 gets cancelled 2 times here. So then you will have 2 VDC by pi. That is the answer. Okay, so root 3 gets cancelled, 2 gets cancelled 2 times here, so 2 VDC by pi. That's the answer. Okay, but I'm giving another important thing here. Assume it is given 180 degree only, 180 degree mode, but instead of star connection, it is given delta connection of the load. Then how to get the same question? Okay, that is nothing but phase voltage. Remember, in case of delta connection, line voltage and phase voltage both will be same. But we didn't discuss anything about the delta connection. But how to get the delta connection things and all from the star connection? Remember, this is very important. Okay, in case of, you can actually take that this is actually star, simple thing, no need to worry much. So you can see that okay, so this is the phase current between the neutral and all. This is line current, line voltage, sorry. Okay, this is line voltage. Now if you rearrange this one as a delta, same thing is rearranged as delta. So now look at that, phase voltage is same, right? So that is the main important thing. That means here phase and line are same. But if you look at that, in case of star, this is the line voltage, this is the phase voltage. But now you can see star line and delta line are same or different? It's the same. So we need to remember here, line voltage star connection and line voltage delta connection is same. Okay, line voltage delta connection, phase voltage delta connection are same. So to get the delta connection things and all, we already have the star connected line voltage equations, Fourier series, etc. Same thing we can get in delta. Once you get the delta, you can use the delta connection things and all. So that's it. Simple thing. Only we need to remember this. Okay. Move on to the next question. In three-phase inverter circuit shown, the load is balanced and gate sequence is 180 degree conduction mode. All switching devices are ideal. The RMS value of the load phase voltage is. So this is what? Three-phase 180 degree conduction. We need to calculate phase voltage. What is the equation for the phase voltage? Okay. So if you remember the equations what we discussed in the previous videos, you can actually get that. Here 180 degree phase voltage, it's RMS value, okay? RMS value, P0 RMS value, phase for 180 degree is, you can take, it is root 2 VDC by 3. Substitute the values. VDC is given in the second question, 300, okay? So 300 into root 2 by 3. Okay. Okay, so 3 gets cancelled here 100 times, and root 2 is 1.414, so that's why it is like 141.4 volts. So this is the answer for that. What's the next question? If the DC bus voltage is 300 volts, the power consumed by the load is. So power consumed by the load is, you can easily calculate. Okay. In case of resistive load, we already discussed. What is that? In case of resistive load, we can directly take that. What's that? Power consumed by the load is. It's a 3-phase system. That's why we need to look at that. 3 times RMS value of phase square into resistance. But in case of resistive load, I naught RMS phase you can take directly, V naught RMS phase divided by resistance. Okay, that's only applicable for resistive load. If you take that equation, you can directly take this one as a V naught RMS phase square divided by resistance. So you can substitute things. 3 into RMS value of this one, you can take like 100 into root 2, that 100 square into root 2 square is nothing but 2 divided by resistance is given here 20 ohm. Okay, 20. So then it is like 10,000. 2 gets cancelled, 10 gets cancelled. It is nothing but okay. So 10,000 0 it is, and then 2 gets cancelled, then you will get 1000 into 3, it is nothing but 3000. That's why it is 3 kilowatt. That's it. So next question, a 3-phase voltage source inverter as shown in figure is feeding delta connected resistive load of 30 ohm per phase. If it is fed from 600 volts battery with 180 degree connection of solid state devices, power consumed by the load is in kilowatts is. So now look at that, a delta connection is given and it is 180 degree. Okay, so just now I told you that in case of delta, okay, generally like first of all you can look at like power consumed by the load is always nothing but it's the resistive. Again I am giving directly 3 times V naught RMS square, phase only we need to take, so square divided by resistance per phase. So that's what we need to. But as I told you that in case of in case of delta, phase and line will be same. That's why it is nothing but RMS value of the line square divided by resistance. We can take that. But just now in the previous question, I told you like how to calculate the RMS value of the line voltage for the delta. That is nothing but RMS value of the line voltage of the star. In 180 degrees, what is the line voltage? That is nothing but VDC into root of 2 by 3. So that's what we need to calculate here. So what is that one? 600 into root of 2 by 3 volts. Substitute that in this case and get the power. So power consumed by the load is 3 into, okay, you can use this one also, that's not an issue. 600 square into 2 by 3 whole divided by, it is 30 ohm. Okay, 30. So you can simplify that. So 3 gets cancelled, and here, okay, so here 30 in 600 cancels 20 times. Okay, so then you will have this one is 24 kilo ohm. Okay, let me verify again. Let's see that. Okay, with this I'm stopping, and in another video we'll discuss about some more gate exam questions. Thank you.